Yes, good evening, and let's continue with our class. We had begun yesterday looking at Lagrange interpolation, and we want to continue with the same concept just from the start. We begin from the start because we had some interruptions yesterday. Now, so as we had said, Lagrange interpolation is just a process of if you are given n plus 1 points, then you are required to construct a polynomial through all those points without leaving any of the points out. Supposing I have n plus 1 points, and I want to draw a polynomial through all of them, then the polynomial that I come up with, the degree of that polynomial is n, will be n. So if I have n plus 1 points, then the degree will be n of or less. So the maximum the degree can be will be n. In other words, if I have 3 points and I want to draw or construct a polynomial that passes through all these points, the polynomial can come up with the maximum degree will be 2. So it's n minus 1, that is. So if I have 3 points, then the maximum degree polynomial that I can have is 2. So that means we can have, if I have 3 points, it will be 2. If I have 4 points, it will be 3. And if I have 4 points, the degree can be, the maximum the degree can be is 4. But we can have polynomials of lesser degree. We're just saying the maximum degree we could have would be n minus 1. Now, again, we say that we cannot draw two different polynomials through the same points. It's only one polynomial that is possible. It's only possible to draw one polynomial through the given points. So the polynomials, the number of polynomials that you draw through those points is unique. You cannot have two different polynomials through the same points, or three different polynomials through the same points. Just one polynomial that you can draw or construct. So therefore, Lagrange interpolation is a technique for creating polynomial that passes through certain set of points. The resulting polynomial that you'll be constructing is what we call the Lagrange interpolation polynomial. So that is when you hear of that, that is just a polynomial you've constructed to pass through given points. Now we say that this technique is very, very important, has various applications. And for instance, you can apply it in numeric analysis. You can apply it in computer graphics, in data fitting applications. And most importantly, in our lessons, it's about the zero knowledge proofs, the snarks, ZK snarks. So this knowledge is very important in ZK snarks. And of course, at the end of this notes, you'll see in my exercise, you try and see the questions I've put there, where you can be applied, and you try and see if you can respond to some of those questions in terms of how it's applied, even before we arrive at those areas to tackle. You can still try and study ahead in terms of applications of this Lagrange interpolation. Now, so how do we construct Lagrange polynomial, Lagrange interpolation polynomial. So first of all, I define, then this definition, of course, will tell us how we'll be constructing, and we look through examples. This symbol is for summation from I is equals to 0 to I is equals to n, and this symbol is product. So let's understand the symbol, the formula. This is the formula for the polynomial. Now it says sum yi multiplied by lix. So you are summing this. What does yi multiplied by li mean? So I is 0 to, so you can have y naught, l naught x, that's what it means, plus, I'm just telling you what this formula means, then plus y1, l1x, then plus all the way up to yn, lnx. So that is what this formula is saying, that the polynomial will be arrived at this way. That if you have L naught x multiplied by y naught, then plus L1 x multiplied by y1 all the way up to that. So what we need to know, therefore, what are these L1 x, L0 x? Of course, they're coming from the points. These are the points given to us. The first point, the second point, all the way up to the nth point. Now, so what is L0? The formula is here. The formula is here. It's telling us to get Lix, we take x minus xj divided by, of course, this is a product. This is a product. This is a product, and we are multiplying from j from 0 to n. J from 0 to n, we are multiplying all those. And j should not be equal to 1. No, should not be equal to I. So what this means, this formula is the same as x minus, let me just write where I can see. So it depends on which point are you considering. Which point are you considering? For example, if you're considering the first point here, which is x naught, y naught, then the formula for L naught x will be x minus, now you subtract x1, x2, all the way up to xn. You don't subtract this. So it will be x minus x1 multiplied by x minus x2 multiplied by all the way up to x minus xn. This is divided by, now you go back to the point you're considering. The point you're considering is this. This is the point. So what does it have? The value of x is x naught. So that x naught subtracts x1, then x naught subtract x2, all the way up to x naught subtract xn. So that's how we are finding L naught. Now you'll come and then find L1, L1x. That means you're now considering this point. Considering this point now, this time round. So again, it will be given by x minus x naught. Now subtract all other values of x naught apart from the value of x that you are considering, the point you're considering, apart from that. So multiplied by x minus x2 multiplied by x minus x3 all the way up to multiplied by x minus xn. Then again, what about the denominator? It will be now the point you're considering, which is x1 minus x0 multiplied by x1 minus x2 multiplied by x1 minus x3 all the way up to x1 minus xn. So this is the value of x1. So we'll come and get x, no, not x1, the value of L1x. And we call them the Lagrange basis polynomials. The Lagrange basis polynomials. Now, so after you've calculated all of them up to Ln x, depending on the number of points you have, you now come and multiply L naught x by y naught. Y naught is just the value of the first point. The y naught, the y coordinate of the first point. Then L1x multiplied by the y coordinate of the second point, all the way up to the nth y coordinate, the nth y coordinate of the last point. You sum all those, and then after summing, of course, you'll have to simplify, collect like terms, then come up with the polynomial. So that is about the formulas that I've given here. And of course, we've said that if you have 4 points, for instance, the polynomial that you'll come up with, its highest degree, it will have at most, it will go of at most degree 3 if you had been given 4 points. If you had been given 3 points, and then the degree is at most 2. And if you have 5 points, and then the degree is at most 4, and so on. And that is what I've explained here under the properties. The degree of the polynomial that you are coming up with is at most n. That is, if you have n plus 1 points, the degree will be at most n. And about the uniqueness, we've said that if you have those points, you can only draw one polynomial through those points. It's only one polynomial that can pass through all those points, not several polynomials. Only one polynomial can pass through the given points. Now, so here I'm just showing you step by step of what we're supposed to be doing. The first thing we've said, of course, we will calculate the Lagrange basis polynomial, Lix. So you calculate for L0 x, L1 x, L2 x, up to the last point, depending on how many points you have. So if you have 3 points, then you are doing L1x, L2x, and L3x. No. If you have 3 points, you're doing L0 x, L1 x, and then L2 x, if you have 3 points. So it depends on how many points you have. So if you have 4 points, then you are doing the extra one, which is L3x if you have 4 points. After calculating this basis polynomial, the Lagrange basis polynomial, we now come and multiply each one of them by the corresponding y value. The corresponding y value. Then after that, sum the results. So let's look at the first example. Just this is the example we're looking at yesterday before we were interrupted by network. Now, so we've been given these 3 points, and we're supposed to construct a polynomial through all of them. Of course, we expect that the polynomial will be of at most degree 2. But we note that this is the x naught value, the y naught value, x y value, y naught, y1, no, x1, y1, x2, y2. So we want to, first of all, find the Lagrange basis polynomial. That's where we begin from. We begin by finding L naught of x. This is the point we are considering. This is the point we are considering. So we take x minus all other x values apart from the x value of the point you're considering. So the point you're considering is this. So this is its x value. So this is the only one we don't subtract. But we'll subtract 2 from this x, then multiplied by, again take x and subtract 3. This 2 and this 3. And then out of, now take this x value. Take that x value, which is 1, subtract the same 2. The same 2, this 2. These 2. We are dealing with the x values. And then take the same 1 and subtract 3. This is the 3 I'm referring to, the x value, not the other 3 in the y-axis. So we've so far we've just been using the values of x. We've not gone to the values of y. Now simplify. Simplify the numerator by just multiplying. That will be x squared, and that will be negative 3x. Just multiplying, and then that will be negative 2x, and then this and that will be positive 6. Out of, if this first bracket is negative 1, and the second bracket, of course, is negative 2. So what do you get here? This will be x squared negative 5x plus 6 out of negative 2. No, positive 2. When you multiply negative and negative with positive. So that's how you get when you simplify. In my example here, I didn't simplify here because I simplified it later. It doesn't matter, you can simplify it even at this point. You can simplify it there. Let's leave it simplified as well, so that we will just carry from here and go with it at the bottom. So we've already simplified this one. But let's just be sure that we've done correctly. We multiplied x, or just it's here. X and x will be x squared. X and negative 3 will be negative 3x. And then x, negative 2 and x will be another negative 2x. So this 2 gives us negative 5. And then negative 2 and that will give us positive 6. Our denominator is okay. Our denominator is okay. So we've already simplified this time, and we'll just carry our result at the bottom. Okay, let's come to L1. We go back and see which point we are considering. This is the point we are considering. So this x is the x value. So L1 of x will be x minus the other values, other x values. This is x1, the other x values are those. Then 1x minus 3. Then at the denominator, now take the x value of the point you're considering, subtract 1 from it, and then take it again, subtract 3 from it. You know what the 3 and the 1 I'm referring to. The same 1 and 3 that you used in the numerator are the same ones you're using in the denominator. Now, so what does our numerator become? X times x will be x squared. Then x times negative 3 will be negative 3x. And then negative 1 times x will be negative x, which gives us negative 4x. Negative 4x, because that is negative 3 and negative 1. And then negative 1 times negative 3 will be positive 3. Positive 3. Now, the denominator has 1, the first bracket, and negative 1 in the second bracket. That is negative 1. So 1 and negative 1, that product is negative 1. So when you take it to the numerator, you get negative x squared, positive 4x, negative 3. And again, we've simplified already, so we'll just carry the result to the bottom. Although initially I had done without simplifying because I was to simplify it later, but there's no problem. You can simplify it early. Now, so We come to L2 because we had only 3 points. This is our last Lagrange basis polynomial that we are doing. Let's go back and see the point we are considering. So we are considering the last point of these 3 points. We note the x values. We have 1, 2, and this other one is 3. So this is 3, and the other one is 1 and 2. So this is the one we are considering, the point we're considering. So L2, x will be x minus 1, and then x minus 2. And then 3, that was the point, the x value of the point under consideration, minus 1, then 3 minus 2. So what you get in the numerator when you simplify, x times x will be x squared. Then x times negative 2 will be negative 2x. And then negative 1 times x will be negative x, which gives us negative 3x. And then negative 1 times negative 2 will be positive 2. What about the denominator? The first bracket gives us 2, and the second bracket gives us 1. So 2 times 1 is 2. You can leave it at that. You can leave it at that. You can say it's simplified, although we know you can go further. Now, we are done with calculating the basis. So what is now follows is to multiply each of these by their corresponding y values. Multiply each of them by the corresponding y values. The first one, the y value, L0 will be multiplied by that, 2. L1 multiplied by 3. And L2 will be multiplied by 5. So 235. Okay, so we had already simplified ours. Let's just carry a simplified one at the bottom. It's x squared minus 5x plus 6. X squared minus 5x plus 6. X squared minus 5x plus 6 over 2. We are multiplying by the y value, which is 2. Then plus, of course, they are even here. But ours had already been simplified. Let's just carry it. Let's carry it. It was already simplified. Oh, it is negative x squared plus 4x, then minus 3. I don't know whether I remember. Negative x squared plus 4x. Negative x squared plus 4x. Negative x squared plus 4x. There was a minus 3. Then the y value is 3. The y value is 3. Then lastly, we have this one that the y value is 5. But what is the simplified one? What was the simplified one? The simplified one is here. X squared minus 3x plus 2. X squared minus 3x. X squared minus 3x plus 2, then over 2. Okay? I was already simplified. So what remains is just to multiply them out and to collect like terms. Of course, you can see that this will cancel with that. So the first one, we have x squared minus 5x plus 6. Then this one, just multiply 3 inside, and you have minus 3x squared. And inside again, you have positive 12x. 12x. Inside again, you have negative 9. Then what about this one? This other one, you have 5 out of 2 x squared. Then minus, you can leave it at that. Okay, let's just continue. So we have negative 15 out of 2 x. Then this other one will be 5. Because it's 5 out of 2 times 2, which is 5. Now the like terms that I'm seeing, this, and these are like terms. And they have a fraction there, the fraction 2.
Excuse me, sir.
Yes.
I think the second term of the
Yes.
polynomial is supposed to be +9.
+9, eh?
Yeah, not -9. Because you're multiplying -3.
Oh, it's +3 here. It's +3 here. The minus we had already distributed inside. Eh?
Oh,
we are
okay.
not using this. We're not using this. We're using our simplified one from above. So the simplified from above, we wrote it here. We wrote it here, and then this is what we are using. Yes, but if you would have been using this, then I think you would be multiplying by negative, but this time it is positive. Have you gotten what you've gotten what I'm saying? Huh?
Yeah. I've gotten what you said. I've seen how it's -9.
Yes, because we had already simplified ours at the above here. The minus was this one at the bottom, and we already distributed it up. So minus into x squared gave us negative x squared. Then minus into this negative 4x gave us positive 4x. Then this minus into positive 3 gave us -3. So the minus has already been taken care of. So this one we decided we now simplify, then we just come with the simplified version at the bottom. Now, so we're looking at the x squared, and we note that the LCM is 2, and so here it's over 1. So 1 into 2 goes there 2 times that, the 2x squared. And then 1 into 2 will be 2 times that will be -6x squared. And then finally we have 5x squared. So this gives us a half or what? But let's continue. Let's continue and come to the one of x. The one of x, so we have this. We have that with an x, we have this with an x, and then you finally have this with an x. And of course, the LCM again is 2. So this is over 1, and this is also over 1. So 1 into 2 will be 2. 2 times negative 5x will be -10x. And then 1 into 2 will be 2. 2 times 12 will be 24x. And then 2 into itself, of course, is 1 times that will be -15x. Now, what about the constants? We have 6. And then we have -9. Then we have +5. So now let's simplify here. The first one, +2 minus 6 will be -4. -4 plus 5 will be 1. What about this one? -10 plus -15 will be -25. -25 plus 24 will be 1. If there's somewhere I'm gone wrong, it's good that you correct so that we proceed with correct things. 5 plus 6 will be 11. 11 minus that will be 2. 11 minus that will be 2. I don't know whether it's the same I was getting. Let me just go to the one I was getting. Oh, it's correct. It's the same that I was getting. But this a sign here. This sign is negative. That sign is positive. Let's just go back. Let's go back and see. Let's go back and see. Yeah. The sign is supposed to be negative because this is -10, -25, x plus 24. X, that would be negative. Supposed to be negative. Supposed to be negative. So you can simplify it from above coming. down as you proceed towards the answer. You can see this is the polynomial we're looking for. This is the Lagrange interpolation polynomial. You can see the degree is 2. This polynomial passes through all those points. You can verify. To verify if it passes through all those points, you can try and, what are the points? The points, one of the points is 1, 2. Try and insert 1 where the x is and see whether you get 2. That is how you prove that it passes through those points. So if you see, we have a point 1, 2. But now insert 1 here where there is x and see whether you get 2. So what we have is a half. Where there is 1, x put a 1, then minus a half. Where there is x put a 1, then plus 2. So the first bracket gives us a half. The second bracket is a half, and then plus 2. And of course, this is 2. So it tells you that if the value of x is 1, the value of y will be 2. That means this graph passes through point 1, 2. Passes through point 1, 2. Because if the value of x is 1, it gives the correct value of x, the correct value of y. Let's try the other point and see. The other point is 2, 3. When the x value is 2, we're supposed to get the y value as 3. When the x value is 2, when the x value is 2, and the x value is 2, we're supposed to get the y value as 3. Let's see whether that is true. This will be 4 divided by that is 2, and this is -1, then plus 2, and this is 3. You can see it gives you the correct value. So it means the graph that we come up with, this polynomial, is true. It passes through those points. So that's how you can verify. Now, if you can even have 1,000 points, you can still draw a graph through all of them. You can draw a graph through all of them, irrespective of where they are located, irrespective of how they are located. You can draw a graph through all of them. And this knowledge is very important also in when we're looking at elliptic curves, and of course you have very many points, and how to get also a graph that passes through all those points. It's a very important knowledge to us. Now, these steps, those who are writing the programs, the steps that I've given are the ones we just use it to write the programs. So the steps, first, your program should be able to calculate the L0, L1, L2, and so on. Should be able to calculate all those. And after calculating all those, each one of them should be multiplied by the corresponding value of y. Corresponding value of y. Each one of them should be multiplied by corresponding value of y. Then after that, you get the summation. You get the summation. So when you're writing those programs, it means the functions. You have those 3 functions, each one of them doing its own work. Then you have the main function, of course, with its work also. I want to look at one more example, then we'll look at the code that I've come up with. And you can, looking at that code, you can see what to modify so that you come up with a code that can even be more, it can have more functions, perform more things, and so on. Now, but the good thing is that you've seen the steps, and are the same steps that we're going to use. I'm just doing this for emphasis. And of course, this, look at this, this formula. I've used n, but how many points do you have? 1, 2, 3. So our n, therefore, is 2. Our n is 2. So instead of this, it's supposed to be this. Is the summation of I is equals to 0 to 2. yi lix. This is 2. So we are summing from 0 to 2. So that is the formula. So, but what I've written here is the general formula that we began with. The general formula we began with. Of course, it's not. We know that n is. If you have 3 points, our n will be 2. If you have 5 points, our n will be 4. So you're summing L0, L1, L2, L3, L4. So that's what we are doing. So the same thing, this one can also change from J from 0 to 2. So you change all of them. This one is for the general one. If the points are running from 0, the 0th point to nth point. But now, if you have only 3 points, n changes to 2. Now, this is the points you've been given. The same procedure. Want to get L0. We're considering this point. This is the point you're considering. So x minus each of the remaining values of x. That's why you see I have x minus 2. Then x minus 2. The remaining values of x, this value and that value. Then take now the x value of the point you're considering and do the same thing. Subtract 2 from it, negative 2. And then again subtract 2 from it. So this minus becomes positive, and that's why you're seeing a positive sign there. This one remains the way it is. And of course, this minus and this other minus becomes positive. And that's why you're seeing 0 plus 2 becoming 2, and then 0 minus 2 becoming negative 2. The denominator becomes negative 4. The numerator becomes this. Of course, we can simplify, and that's what I did here. Multiply that, get x squared. Multiply this, get negative 2x. Multiply this, have positive 2x. Then multiply that, you have negative 4. So this 2 gives you 0. So you're left with x squared minus 4. And the denominator has negative 4. So that negative is the one I've just put here. It's no problem. The one I've just put here. So you've simplified that. This one I decided to simplify up to the end and move with it just like that as we progress. These are very interesting concepts, There are a lot of applications. Now let's get L1 of x. Let's go back to the points and see what the points were given. Oh yes, this is the point we are now considering. So we'll subtract the other values of x from x. We'll subtract 0 and 2 from x. Subtract 0 and 2 from x. That's what we are saying. Subtracting 0 and 2 from x. And then the value of x of that point, the value of x that we're considering was negative 2, I think. It's negative 2. Now subtract the other values of x from it. Subtract the other values of x from it. So negative 2 minus 0 and negative 2 minus 2. The numerator, the first bracket, x minus 0 gives us x, then x minus 2 remains. So of course this you can simplify, or I didn't simplify, but there's no problem, you can simplify that. The first bracket at the denominator is negative 2, and the second bracket is negative 4, which comes to positive 8. So I left at this because I saw this one was easy to simplify even later. It's easy. So we come to the last L2. L2. Go back to see what points we are given. We are considering the last point, this last point. So the value of x, subtract this and that. And then come and subtract the same things from 2 at the denominator level. So 0 and -2, 0 and -2, 0 and -2, subtract from x. And then the same 0 and -2 subtract from 2. Now let's work with the first bracket on the numerator will be x. And the second bracket, this L minus and minus will be positive. So again, I left the numerator that way. The denominator, the first bracket will be 2, and the second bracket is 2 plus 2, which is 4, and that is 8. So again, I thought that would be simple to simplify. So I left it that way. Now I go back now, since I have the values of L1, L0, and L2, I go back to obtain their corresponding Y values. Their corresponding Y values. So I have 4, I have 1, and I have 3. 4, 1, and 3. 4, 1, and 3. So 4 will be multiplied by L0, 1 by L1, and 3 by that. So of course I have those L0. L0 is where was it? L0 was here. It's -1/4 x squared minus 4. Then I have L1 here. Then I have L2 here. I just multiply them by the corresponding values of y, and that's what I'm doing at this point. That's what I'm doing at that point. So then at this point now, I just want to simplify. I just want to simplify. I note that this and that cancels. So that the first part here, I'm left with the negative into x squared minus 4. And this other one, I can leave it at that. I can leave it at that. So this one, I can just open this bracket by multiplying by negative inside. And then these other two, they have a common term. Of course, this common term, this denominator, I can even extend it to this other side. But while I was doing it, I didn't. So let me just do the way I did here. Of course, you know that this one has to come inside the bracket. And this is 8, 8. So there's nothing to multiply with. It's just 8. So this will be x squared minus 2x, x squared minus 2x. And this other one, this x squared plus 6 plus x, this is x squared plus 2x, but then there's a 3 here, which gives us a 3x squared plus 6x. Now, the negative 2x and the 3x, no, the x squared and the 3x squared gives us 4x squared. Then negative 4x, no, negative 2x and 6x gives us 4x. So at that point, again, you can extend this denominator. You can extend this denominator to the other values so that we have the like terms coming together. That is one way. The other way, you can just split. This fraction. That's what I think. That's what I did. No, did I do that? Oh, I didn't do that. What I did was I factorized. I factorized 4 outside. So this one is like, this other one is like 4 into x squared plus x, then out of 8. So this one goes here 2 times. So that's what I did. So that I then have negative x squared plus 4, and then plus x squared plus x out of 2, then I collected like terms. No, I put them under the same LCM, which is 2, and this is like over 1. Like over 1. So 1 into 2, 1 into 2 will be 2. 2 times that would be negative 2 x squared, then plus 8, then plus x squared, then plus x. So when you collect like terms, of course it's out of 2. So negative x, 2x squared plus x squared will be negative x squared. Then plus 8x, then plus 8 out of 2. I left it at that. This is the polynomial we're looking for. And as I've said in the earlier question, you can always prove that you are right by trying to insert the values of x and see whether you get the corresponding values of y. That is how you prove that your polynomial is correct and is passing through the points. That's how you prove that. Okay. So we have this code. This is the code. I think there's another example after the code. I wanted this example to come before, but since the code has appeared, let's look at it. So of course, as we said earlier, you can always change this. So we've said I32, because we are dealing with the both positive and negative numbers. So we talk of I32, where 32 means bits, 32 bits. If you were to deal with only positive, maybe you will then be dealing with the U32 and not I32. So it's mutable. So the result, let the result be mutable, and you make it be 0.0. So it will be changing. That point, that result is not static. It will be changing from time to time. Now, the y values. So let again be mutable, and you initialize it at yi. I will be changing. I'll be changing. And look at this. Look at this. It says, if I is not equal to j, if I is not equal to j, this is what this function is. Sorry, this is how you read this. This is how you read it. If I is not equal to j, so you see that is a loop. You go inside that loop and then do what is inside the loop. What it says that then the term will be x minus xj. And remember that this j is changing. It will be, for instance, if we are looking at the first point, we're looking at the first point, and then that's what we've already done. What it is talking about here, it is x minus x naught. No, if the point is x naught, then this will be x1, and then multiplied by x minus x2, and so on. Then it says over. Can you say that? Over. Now the point you're considering, take its x value and subtract the other x values. Subtract x1, for instance. So if you supposing this was x naught, then we'll subtract x naught again minus x2, and then all the way up to and so on. So that is what it's saying here. That's what it's saying. That's what this formula is saying here. And what I said is once we know this formula, once we know the formula, that's what we just wrote. Then we increment the next value, increment the term. So you see, we began by considering the point x naught, x, the first point. We began by considering the first point. So now increment, go to the next, consider now the second point, for instance. Consider the second point. That's what it's now saying. And do the same. After you've done the same, again increment until you arrive at the last value. And you see what you increment, the result is changing, therefore. The result is changing every time. It was mutable, it began by that. So when you get the first result, it goes there, this result changes. When you do increment and come to this point, again calculate, you get another value, again that changes. That's why I say it's immutable, meaning it's not permanent, it's changing. Once you've done all those, you come up with the results. Once all that is done, you have the result. So the result are all those put together. So this was a very short, code. It's a very short code. Of course, the main function is here, where you put your values, and after inputting your values, it calls for the Lagrange interpolated value. Now you see this code, what this code is doing is not giving us the polynomial. This code is calculates the polynomial. Then after calculating the polynomial, if you give it the value of x, it will give you the corresponding value of y. Give it the value of x, it gives the corresponding value of y. This is what this polynomial, this code is doing. That's why I said this Rust program implements the Lagrange interpolation method to estimate the value of a function. That is, to estimate the value of y at a given x value. And I have another one. I have another code that will come after the two examples. That one now, you give it these values and it gives you the polynomial. It gives you the polynomial. So let me share this first one, first of all. Let me share this first. This first one is this. This is the polynomial, the code I'm referring to. This code, you give it points. After giving it points, it calculates the polynomial. Then it does not give you the polynomial. But now, if you give it the value of x and ask for the value of y, it will give you the value for that respective, value of x. So for instance, I've given it this point, 0, 4, negative 2, 1, and 2, 3. Then I run it. Oh, excellent. Of course, I've asked after running it, I've asked it to give me the value of x, when the value of y when x is negative 2. This is what I've asked. I've asked it, give me the value of y when x is negative 2. So I run it. It tells me when x is negative 2, the value of y will be 1. That's what it's telling me. What about, let me now ask it to give me the value when x is 1. When x is 1. Because it's a polynomial, you've drawn a polynomial and you just want to know what will be a value of y. In fact, you can begin with the x values and then you join in to draw the polynomial. You ask it for the values of y's, and then you join the polynomial. So I've asked it now to give me the value of x, when the value of y when x is 1. It tells me that when x is 1, y will be 4. Y will be 4. You see this? You see, since this is 3 points, what we came up with was a quadratic equation. So we just asking it, this quadratic equation, what will be the value of y when x is 1? What will be the value of y when x is this, and so on. So it's just giving you now. Let me ask for a bigger point, a bigger value, and see what it will say. When x is 8, for instance. It has told me that the value of y will be negative 24. The value of y will be negative 24. So if you have this, then it becomes very easy for us to draw a graph, if you even on a graph paper and so on. Now, so tomorrow I think we will be looking at the same concept, but now we will be looking at mode P, and that is very important to us when we have mode P. Of course, in terms of security, we love our things to be mode P, where P is a prime number for security reasons. Now, this is the other example, and I will just put it for emphasis. I'm not going to go through it. We know that L naught x, this is what it will give us. And of course, just taken the value of x minus, because this is the point under consideration, the first point. So we take the value of x minus this value, then x minus this value. So that is what you are seeing, x minus 1, then x minus 2. Then you arrive at that. And then take the value of x of this point you're considering, which is 0, and subtract the same values you subtracted in the numerator. So it will be 0 minus 1, then 0 minus 2. And that gives you minus 1 times minus 2, which is 2. So you can see, just for emphasis so that you can see it. So I've omitted very many formulas so that you can see now. Very close to the points without going back to check. Now, L1 of x, we are considering this point. So take x minus the other values of x, So x minus 0, x minus 2. Then take this value of x of the point you're considering, minus the same values you subtracted from above. So it will be 1 minus 0, 1 minus 2. Gives you that. Then you move to the last point. Now considering the last point. This is the last point. Now using this last point, take x minus this and x minus that, as you see. Then take the value of x of the last point, which is 2, subtract the same 0 and subtract 1. You arrive at that. Then after that, this is L naught of x, subtracted from multiplied by the corresponding value of y. This one multiplied by the corresponding value of y. And this one multiplied by the corresponding value of y. Then after multiplying by the corresponding values of y, add the results and simplify your polynomial. Collect like terms. So that is what I'm doing in the next step. I'm just multiplying by the corresponding values of y, and you note that the last value of y here was 0, so 0 times anything here will be 0. So I'm only then concentrating on these two. And then when you simplify them, you come up with the polynomial. When you simplify them, what you come up is the polynomial. And this is the polynomial. This is the polynomial, simplified. Unless somebody has a problem with how to simplify, then we can go through it. But this, when you simplify collect terms, combine the fractions. So I was simplifying each one of them separately, so that even when you are alone, you can see that. I was simplifying each one of them separately. I didn't combine them. I simplified them first of all. For instance, this first one, I'm simplifying it here. Then I come to the second one, again simplify it. Then after simplifying, I decide how to collect like terms. Okay, the last question now is what I had illustrated earlier. You're given the polynomial and you're told that it's obtained by Lagrange interpolation from these points. And you're asked to verify that this polynomial passes through the points. Verify that it passes through the points. So this we've done it earlier. Just take the polynomial and insert the values of x and see whether you get the corresponding values of y. So for instance, if I take the polynomial and insert these values of x, which is 0, get p0. Where there's x, I'm just putting 0. Everywhere there's x, I'm just putting 0. When you do that, the first, this one gives you 0, this one gives you 0, and you're left with 1, which agrees that when x is 0, y will be 1. Then you cut the second, check whether what you get when x is 1. So just where there is x, put 1, where there is x, put 1, and you find that. Okay, that's how you do that. So I think that is what I wanted us to look at. Then just share now the polynomial, the code that will now be giving us the polynomial. You give it the points and it calculates the polynomial for you. This is the code. And I've said this Rust program calculates the Lagrange interpolation wants to misbehave. On our last, very last, when I'm just sharing the last thing, it begins to misbehave. But now, at this point, I decided just to define what Lagrange interpolation is. I said it's a method of constructing a polynomial that passes through a set of known points. So this is the code. This is the code. You can, and this code I've given it points. I've given it titles, every point. Here, I'm just importing this, and I've said this one's give the structure of polynomial terms. The structure that will hold the polynomial terms, the coefficients, that is. Then here, implementing the polynomial, create a new polynomial. You initialize with 0. Then there's this, I've said you create a polynomial with a single term. And then there's one here to two polynomials, add 2 polynomials. That is after after simplifying, then you are supposed to add, then multiply polynomial by another polynomial. Then there's this multiply polynomial by a scalar. Then there's this create a polynomial of the form x minus that. So these are various functions. You'll find that not all of them are used to create this polynomial, but I put them there. Others, they were assisting me to do other functions. Then there is this Lagrange interpolation function. This is the main one, the main part, the one that will be doing all the calculations we've been talking about. So this is the one that is doing all those calculations. You can see this, when I is not equal to j, then you're doing the calculations that we've been talking about. But the denominator will be this one, xi minus xj. That is x naught minus x1 multiplied by x naught minus x1 multiplied by x naught minus x2 multiplied by x naught minus x3 and so on. That is what this formula is saying. This is the denominator. That's the denominator. And then we have this, the term. What you get in the numerator divided by this. Then you add, no. This is the y value. The y value multiplied by whatever you have gotten multiplied by the y value. Then you are adding the results. You are adding the results, all of them, to get the result. So what this is saying is, what they were just saying, you have y naught and you multiply by the L naught of x, and so on. In short, this is what it's saying, to get a term there. And then y1 multiplied by L1 of x, and so on. That's what it's just saying. That's a short way of doing that. Let me share this before the network again misbehaves, before we see the code. And just before that, there's this exercise. I said you look at it. This exercise, I'm interested in to see how you will answer this question 5, which says, explain how Lagrange interpolation is used in Shamir's secret sharing scheme. Use an example. This secret sharing scheme, we've not looked at it, but you can look at it in advance. Of course, we will come there. I wanted us to see that Lagrange interpolation is used there. And as you research on that, you can see how the Lagrange interpolation is used in this secret sharing scheme. Then I've said you can use an example to illustrate how the secret can be reconstructed. Now, this question 1, define Lagrange interpolation and explain how it's constructed. So this one is just going through the steps we've already in our examples, just telling us those steps and so on. Then number 2, discuss practical applications of Lagrange interpolation in areas of numerical analysis, cryptography, and error correcting codes. So this one, again, you can research. Some of them, when we reach there, we'll be again emphasizing. But if for the sake of researching and getting to know ideas earlier, we can do that. We've done a question like this. These are the questions we've been doing. Then there's this. I said that if you have 3 points or n points or n plus 1 points, the graph that can pass through all those points is just unique. Is 1. And the question is, explain why Lagrange interpolation produces a unique polynomial for any given set of points. So you think of that. Why is it possible that only one graph can go through all those points? So you think about that also. Okay. So I can now share the code, a polynomial. Give it. Now this is, so the main function is here. I've given it the points. Look at what it prints. It prints the polynomial. Let me ask you to print the polynomial that passes through those points. Yes, it tells me, and we had done this question. And we got negative a half x squared plus a half x, then plus 4. Negative a half x squared plus a half x, then plus 4. It has given us the polynomial. You can change these points to anything you want. Change the points to anything you want, and it gives you the polynomial. Even this one can be 14. So it can be even 14. This can be even 20 what? Can be even 5 or 3. This one can make it 17. Can make this one 20. This one can make it 33. And we ask it to give us a polynomial. So I said, you don't need to arrange your points in any way. Just any points where get a graph that passes through them to start arranging them. A graph is 0.44 plus 0.5